So here, just as a recap, we have seen the 5 main components of reinforcement learning, which are the agent, which is analog in machine learning to what we call a model. The agent is the decision maker. It's the one that will take decisions. Then we have the actions, which are the decisions that the agent will take. So it will take the necessary or what is considered to him the best actions to take. We have the states. Given those actions the agent takes, how the environment is going to change, it will give us a new state. The reward, which is feedback to the agent about his actions. If he did a good action, we will give him a good reward. And if it did bad, we will give it a penalty. And we have the policy, which allows the agent to choose the best actions to take. So now, just before moving forward, does anyone have any question or anything they didn't understand? I will be happy to go back over anything before moving forward. You can write in chat or you can even activate your mics. It's okay. I would love to hear your voices. And if everything is clear, please let me know about that. Okay. Thank you. So now how to approach when we have a specific problem, how to use how to apply the reinforcement learning approach, or how to formalize our problem as a reinforcement learning problem. The very first thing and most important thing is to define the goal. So what do we know that the agent's goal is to maximize the total reward, but the total reward for us, what would it be? Do we want our car to go from pickup place to drop-off place and to do it in the minimum number of steps? It will keep the passenger safe. Or do we want our drone to go and pick, like, let's say, a very dangerous object and explosive objects from a certain position and do that with care? So we really need first to define our goal and see how to transform that into what the agent can understand, meaning in terms of rewards. So we want, for example, if we are our main concern is time, we will make sure to have our agent do that in the minimum number of steps. So for each extra step the agent will be taking, we will be giving him a penalty so that it will do the minimum number of steps. The second thing to consider is the environment. So we can ask ourselves many questions. For example, if we have our action space, is it a discrete action space or continuous action space? Meaning, can I denote every action I have in the environment? Say I have 100 actions, 10 actions. Can I specifically know what are they? Or I have a lot of variables and the amount of variance is very big and I cannot have specific values for each actions. So I need to have a continuous action space. So, and then say for the states, how many possible states do I have? As we saw, for example, in the game of chess, we can have 8 by 8, which is 91 possible, sorry, not 91. We have, if it's an 8 by 8 chessboard, we have 64 possible states that the agent can be at. So these things are to consider in the environment, not just only these two things, because these are the basic elements of our environment. We can have more complex things to consider. For example, if you have extra information that will help the agent, we can also include that in the environment and the state. One of also the very important things and concepts, and that takes a lot of time and a lot of efforts to come up with, is the reward. There are a lot of problems when what we call shaping the reward, because knowing the reward formula, getting the best one, is the key to having very well, then performing very well. So let's say one of the questions is, does the agent have multiple final states? Meaning one final state is one of the states that we want the agent to go to, and in which it will receive a positive reward. So do I have only one? Meaning the agent can only get a good feedback, a big good feedback only at the end, only once, or it can have it many times. Then the thing we talk about time. Does the agent need to get to the goal as quickly as possible? So for each extra step, we will be penalizing the agent. What are the compromises? What are the trade-offs? Do I need safety over time? Do I want bigger rewards over safety, etc.? And are the future rewards as important as the immediate one? And this can be controlled using the discount factor we saw earlier. The bigger the discount factor, the less important are future rewards. So this, what we talked about, both the environment and the reward, this can be done to what we call, there is a library called OpenAI Gym. So OpenAI Gym is the most common way. Actually, it's a tool, it's a library that allows us to build different environments. It's the most common way to implement and use the environment. Because different environments have different observations and different action spaces too. So it's very time consuming and impractical to reinvent everything from scratch for each different algorithm. And also we won't be having baseline to compare to. So let's say we have two researchers, and then they are working on the same problem. And one is creating its own environment like from scratch, and the other one is creating the whole environment from scratch, each one of them in their own way. We won't be having a baseline to compare to, since they even not have the same structure of the environment. I'm not talking about the design, the components of the environment, but the interface of the environment. Some functions can be applied in that environment, and some functions cannot be applied in that environment. But the design of the environment is one also of the key, one of the keys to have what we call a good breakthrough in reinforcement learning. This is where GYM, for abbreviation, come into hand. Like, it provides a standardized interface for the whole reinforcement learning process. It provides also a suite of environments that are already implemented for common situations. It has one for the Go game, for the chess, for certain environments like teaching a robot how to walk. And also it gives you the ability to create your own custom ones. These are the main functions it implements, and that are necessary when doing your own custom environments, or they are necessary to know when you are using an already existing environment. So we have the initialization function, the init function, which is used at the very beginning, of each episode. As we said, episode is from the very beginning to the end. It's used to initialize the environment. And then during training, the agent will pass actions to the environment through the step function. and it will receive a new observation and a reward back from the environment. These action and observation spaces are also defined in our gym environment. We have also the reset function, which is used at the beginning of the episode. Sorry, for the init function, it's only used once at the very first beginning, and the reset is used at the beginning of each episode. Sorry, I inverted the two. We also have the close function, which is called when the learning process is finished, and this to terminate the environment properly. And we can also eventually use a render function, it is not required, to help us to render the environment, meaning have a visual of the environment to better see how things are going. Also, then for our problem, we need, so that was how we formalize it, how we formalize the environment. Now for the decision maker, which is our agent. How am I gonna build it? So first I need to see, do I need a deterministic or stochastic policy? Do I want to have just one action, or I can have probability of action that I can experiment with and change probabilities accordingly, and I can have the trade-off of exploration and exploitation. So would be having a small table enough? This is one of using table is one of really famous algorithms in reinforcement learning, which is Q-learning, so where we store information about episodes in tables, but then it faced a problem, which is for when we have big number of states, we cannot store everything in table, because then table will just explode, and also it will take a lot of storage. So that's from it came DQN, which is deep Q networks, which is comes to the third question: do I need neural network? Because for neural network, we will be having function approximation, and instead of storing everything in the table, we will be using the neural network to output either the probabilities or the best action accordingly. And then for the neural network, if I'm going to use neural network, what type of neural network do I need? Will I be using convolutional neural network, which is for the game of Go the case? It takes a picture of the board, and then it will go through a convolutional neural network and output the specific actions to take, or just a simple feed-forward network will be enough. And then what framework will I be using for building this network? Might be using PyTorch, might be using TensorFlow, depending on what also I will be needing later. What I mean by that is more specifically in the training. So the training is when we have all these components at hand, and we need to make the agent in interaction with the environment. So one of the questions we may ask ourselves when we have a problem and we want to train our agent with the environment we have based on that problem. So should I be using a framework here? By framework, I mean training framework, not like TensorFlow or PyTorch. Those are frameworks for building neural network. So here for the training, should I be using a framework or just a simple algorithm? What training algorithm I use? As I said, I already mentioned two. For example, we have Q-learning and the DQN, deep Q networks. We also have PPU, we have actor critic, A2C, we have many algorithms. Some of them are more suitable for simple cases, because if we have a simple problem, we don't want to use just a very complex algorithm that we cannot debug. And if there are eventually any problems, we cannot find where is the problem. So it's really good and best practice to always start with the simplest algorithms, and the one that would work, and see how the agent would perform. If it's not enough, we will do some hyperparameter tuning. And if it's not enough, we'll go to a more complex algorithm, or even change the algorithm completely. And then also Do I need cluster thus do distributed training? Because reinforcement learning applications are really compute intensive and they need a lot of time. Sometimes it will take even a whole week on cluster. So let's say cluster of 4 nodes. And then if it was in a computer, it will take but around a month or so. So they can really be time consuming, but also depending on the complexity. We can have a simple reinforcement learning agent with just a simple environment and a simple algorithm, which may take a day on our computer. But for like really big applications, even those who are meant for production, even on clusters, it may take a week or so. So one of for the training, this is an example of just a simple algorithm instead of using a training framework. So we will be just doing simple programming with if, else, then. So if here we say initialize the agent, we will be just having an instance of the agent's class, and then we will be looping through a number of episodes we have defined, and we will be resetting the environment, which is using the reset from OpenAI Gym. If we, of course, use our environment with OpenAI Gym, which is something recommended to do. And then just follow algorithmic approach for doing the training algorithm. There are also the frameworks which can be very helpful. I chose to present to today one of the very known ones. It's RLib. Actually, it's an open source library in Python, which is based on Ray. Ray is used for distributed learning in anything, not just in reinforcement learning. And having RLib based on Ray, meaning that we enable also reinforcement learning to be distributed over a cluster. And also like to scale up and even in a bigger cluster. Because Ray provides the foundations for parallelism and scalability, which are simple to use, and also allow Python programs to scale anywhere, like from, if we start just for a laptop, for testing, and we can go to a very large cluster. Also through the RLib developer community, many different algorithms and frameworks are being more and more integrated into this library. So it becomes even simpler to evaluate the performance of different alternative approach. And also a good thing is that it includes implementations both in TensorFlow and PyTorch. The thing is that, as I said, for example, if I want to compare different algorithms, let's say between DQN and PPO, this library has them both implemented this algorithm. I will only need to create the environment using OpenAI Gym. I will have, if my agent is a model, I will create the model. I will just give it the environment and the model to what we call this trainer, if it's a PPO trainer or DQN trainer, and it will do the whole process for me, the whole training from the agent taking action, updating the weights, etc. This library and the training algorithms it has takes care of all of that. Another framework is what we call stable baselines. Actually, the objective of stable baselines is to try to be a scale-learn library, scikit-learn library in machine learning. It tries to do analogous things for reinforcement learning. It provides a common interface, which is based on OpenAI baselines. It gives useful wrappers, for example, for pre-processing or even multi-processing. But I would say Ray is more suitable for when we have cluster and we want to scale up, but it also provides a variety of train algorithms. So she's the same key for stable baseline, just maybe it may be weaker from the scaling and distributed side. They also allow, both of them allow hyperparameter tuning, like the batch size we want to train on, discount factor we saw earlier, the number of training iteration, etc. Although it's true that reinforcement learning has done a lot of breakthroughs in the recent year, and it's getting to be more and more known, it's still a somewhat new field, and it has a lot of challenges. So the main challenge for reinforcement learning is preparing a simulation environment, the environment we have been talking about. It is highly dependent on the tasks to be performed. So we will be really needing to do a specific environment for a very specific task. And OpenAI Gym helps us doing that to be standardized in a way that it will implement all the function and it has the same interface with all the different environments. Let's say, for example, for the game of chess and Go, and even Atari games, preparing the simulation, the environment is relatively simple. But when it comes to building a model that's capable of driving an autonomous car, building a realistic simulator is crucial. It's like really important to pay attention to all kinds of details in this simulator before letting the car go to the real world. Because the cost of that is, it can even cost lives, not only damages and all. So let's say, Joe, you have the simulation, the simulating environment. You can afford to lose 1,000 cars there, but in the real world, you cannot afford that. You will not be also losing just cars, but you can also lose lives. So it's very important to have a simulation environment and to really try to mimic the real world as much as possible. The second problem is a credit assignment problem, especially in games where we get the reward only at the end. For example, for the game of chess, the agent won't be receiving reward until the end of the episode, because as it plays moves, it doesn't know if the player won or lost. So it needs to wait till the very end of the game so that it knows if it was a win or loss or tie, and it will receive the reward then. But when the agent will see back what it did, it wouldn't know what specific actions caused that win. So this is called credit assignment, when the agent cannot know what's the specific action that led him to that result. But through repetition and doing a lot of episodes, the agent can eventually have an approximation of what's the correct path to take. And the third challenge is that, as I said, it can be really compute intensive and time consuming. It takes from days, sometimes to weeks, to months. It depends on the complexity of the project and also the compute power that is provided. Thank you for listening, and I'm open for any questions you have. I'll be happy to go over anything we went through.
Thank you very much, Narimane. Thank you very, very much. Your presentation was really so clear. And thank you again for accepting to join us and explain this new, very new field, reinforcement learning. So please, participants, if you have any question, please ask. Actually, Narimane, I have myself one question.
Yeah.
So my question is about classification models. So let's say that I am using a deep learning model for a classification task. And then I wanted to, let's say, to measure its feasibility in after production. I mean, after using it on mobile apps for the users. So is it possible to use the reinforcement learning? Is there actually a kind of this study in the literature saying that you are researching in reinforcement learning? I mean, is there any combination between deep learning and reinforcement learning?
Yeah, of course. So the agent itself can be a deep learning model. So, but the thing with the reinforcement learning is that it helps us with decision making. So we may be using deep learning, for example, for classification, but then the reinforcement learning part will be to take action based on that classification. So if I have a specific output, let's say the image classification, you know, it's this kind of image. So I should be taking this action when I have this image. So this is where the reinforcement learning will help us in taking decision based on output.
Could it be until?
Sorry, I didn't hear you. Could it be what?
Decision on which is the.
Hello?
Yes. Could it be model to use? Yeah. Can you hear me right now?
Yeah, now I can hear you. Can you please repeat?
Yeah, I was saying that could it be used to decide which model is the best? Let's say I'm having a group of models, many models, and then I want to decide which is the best one in the specified task. Could it be possible to use? Yeah.
And the model, you want to use it for reinforcement learning, or you want to use it, for example, for the classification task?
No, it is a model for a classification task. Yeah.
Actually, it can be used like you can do that without reinforcement learning. I guess it will be simpler. You can because for reinforcement learning, if you wanna like know what is the best model, you will also be needing to have a model to predict what's the best model. I wouldn't say it's impossible. It's possible to do that. You can use it. Just I don't know if it will be efficient because as I said, it may take a lot of time to train. So I guess it would be better like if you try with each model. This is kind of, if it depends if you have a big number of models, but you can try with different models and compare the performances. This can be done like with Python script, but it's possible to answer your question. It's possible to do it with using reinforcement learning. It's just maybe too intensive and can't be not efficient.
Okay, so my idea is just about a classification model which is in the production level. I mean, it is used by users, and then it may be reward if it gives a good decision, and or it may be punished if it gives a wrong decision. So this way I was thinking about.
Yeah. But like once the model is in production, we are no longer iterating, right? So we won't be using the reward and all once we are in production, because we use the reward for the training phase so that we can learn the optimal policy. And then when we have the satisfying results and we can know that we have reached that optimal policy, we will take that optimal policy and deploy it. We won't be like in production, we won't be using the rewards at all. It's just to make the agent learn.
Okay. Okay. So very clear, Narimane. Thank you so much.
Thank you.
Okay. So, dear participants, if you have any questions, Otherwise, we have Narimane with us on Slack. So yes, Narimane, could you please share your presentation on Slack?
Okay, sure. I will download it and upload it to Slack. Yeah.
Participants, yeah. And okay, very much. So participants, if you have any questions, please ask also on Slack. Okay. Hope it was clear enough. So maybe we should stop right now.
Okay.
Okay. So thank you again, Narimane.
Thank you.
It was a pleasure having you on board. It was really a pleasure. Yeah.
My pleasure.
So yeah. I mean, I needed too much to know more about reinforcement learning, and I guess all the participants, or the majority of them, were new to this field, and I hope it was beneficial for them. Okay. Thank you very much. Yeah. Thank you. Thank you.
Thank you.
Have a nice day, Narimane. Have a nice day, dear participants, and see you tomorrow for our next session.
Thank you, and best of luck to you, and to all the participants for what's coming.
Thank you. Thank you. Goodbye.
Bye.